Okay, so this video is going to start introducing you to finding what's called the interval of convergence. Uh, and I'm calling this preliminary because we're not actually addressing the entire interval of convergence here. The interval of convergence is what x's can I plug into a Taylor polynomial and say it gives me a good estimate. So um, more formally, it's the interval in which the x values will cause an infinite series to converge. And what we're going to be talking about is finding what I tend to call the preliminary interval of convergence, in that we're not going to be discussing the endpoints this time, because the endpoints get a little complicated in that sometimes the endpoints converge and sometimes they don't, and sometimes they only converge sort of. And that will make sense when we get to that. That's one of the last things we'll actually talk about. So just for now, think of the interval of convergence as what are the x's that are close enough to the center to give me a good approximation, or that formal definition of the interval are the x values that cause the infinite series to converge. So to find this preliminary interval of convergence, we're going to be using what's called the ratio test. And the ratio test is specifically set up to look at the absolute value of our term. So even if we have an alternating series, what we're going to be looking at is always positive. And this is what's called absolute convergence, which is a good thing for us because if the series of absolute values of terms converges, then the regular series has to converge. So it's actually really strong, and it's something we want to have happen with a series. And the idea of this is we do a limit as n goes to infinity, where we compare the n plus first term to the nth term. And if that limit is less than 1, the series will converge. If the limit's greater than 1, the series diverges. If the limit equals 1, it's actually inconclusive and we can't do anything about it. But in terms of finding our preliminary interval, it works really, really well. So examples. None of this makes sense until we have examples. So I want to find the preliminary interval of convergence for the series where we're summing n goes from 0 to infinity of n times x to the n over 10 to the n. So I'm going to be doing the limit as n goes to infinity of the absolute value of the n plus first term. So I'm going to have n plus 1 times x to the n plus 1 over 10 to the n plus 1 compared to the nth term, which is just the general term the way it's written. I will admit this is not a way we would typically write this. We would typically go ahead and kind of automatically start at what my next step here is going to be, in that it's difficult to look at this as a fraction compared to another fraction. So we're going to take the big fraction bar and treat it like division. So I have my n plus first term times the reciprocal of the nth term. Now, what we're going to want to do here is we're going to want to group anything that's based on n in its own little fraction. Anything that has x's or anything that has the tens can go in a different fraction here. So I'm just going to do some rearranging. So I have the limit as n goes to infinity of the absolute value. I have an n plus 1 over n. And then I have x to the n plus 1 times 10 to the n over x to the n times 10 to the n plus 1. And the reason we want to kind of separate those out is according to the limit, n is the only variable. It's in terms of the limit, n is the only thing that changes. So even though x is a variable, it doesn't change in my limit. So the x can be treated like a constant since the limit is all about n going to infinity. So doing some simplifying then, the limit as n goes to infinity, the absolute value of n plus 1 over n I'm going to use some properties of exponents. X to the n plus 1 is really x to the n times x to the first. And 10 to the n plus 1 is really 10 to the n times 10 to the first. So that's going to allow me to do some canceling, in that I can cancel an x to the n, and I can cancel a 10 to the n. So what I'm going to have left is an x over 10. Now, the x over 10 is a constant since there are no n's involved in that. So I have the absolute value of x to the 10 can be pulled out of my limit because the limit is n is changing. Now, I can do, as I look at this, as n goes to infinity, n plus 1 is going to infinity, n is going to infinity. So I can do L'Hopital's rule. And I still have the absolute value of x plus 10, which is a constant in terms of the limit, times the limit as n goes to infinity of 1 over 1. And what I get is the limit of 1 over 1 is just 1. So I have the absolute value of x over 10 is what my limit is approaching. Well, the absolute value of x over 10 needs to be less than 1 for the series to converge. I can solve that. So to get rid of the absolute value, that means that x over 10 needs to be between negative 1 and 1. Multiply everything by 10. And here is a preliminary interval of convergence. This means that if I pick something between negative 10 and 10 and plug that in for x, the series will converge. I won't have to check that again. Those are good x's. So if I say I want to use, I'm going to take from the series and use the first 6 terms to approximate my sum, well, as long as x is between negative 10 and 10, that would be a good estimate. And I could then use the Lagrange remainder to estimate its error bounding. One thing that we do not know is what if x equals 10 or if x equals negative 10. We don't know about the endpoints yet. That's something that's going to come up in a later lesson. If I then do a second example here, this is something that's going to happen every now and then. And it's to illustrate the fact that a series will always converge at its center, because remember, the center is like the point of tangency. It is a point that is both on my function and on my Taylor polynomial, no matter what. It's as I move away from the center that I start to diverge. So I'm going to find the preliminary interval of convergence for this series. So that means I'm going to be doing the limit as n goes to infinity of the absolute value of the n plus first term compared to the nth term. Well, I already talked about the fact that x to the n plus 1 is the same as x to the n times x to the first. But n plus 1 factorial is n plus 1 times n factorial. So I can now do some canceling here. So n factorial will cancel, x to the n will cancel, and I'm going to be left with the limit as n goes to infinity of the absolute value of n plus 1 times, times x. That x is, or the absolute value of x, is a constant since the limit is as n is approaching infinity. So I can take the absolute value of x out, and then I'm times the limit as n goes to infinity of the absolute value of n plus 1. But that limit is going towards infinity, and no matter what x is, times infinity I'm approaching infinity. It's impossible to have that be less than 1. So that means that this series diverges for all x's except its center, which in this case, I'm not subtracting anything from x, so the center is 0.